You know, we've all seen the bell curve, right? It's that perfect, neat, symmetrical shape from statistics class. But here's the catch. In the real world, especially when you're talking about money and finance, data almost never behaves that nicely. So, what happens when the data breaks the rules? That's exactly what we're going to get into.
So this is the classic, the perfect normal distribution. The peak is slammed right in the middle, which means the most likely outcome is the average one, and then it just slopes down perfectly evenly on both sides. It's clean, it's tidy, and it's almost always our starting assumption. But, of course, real life is messy. Things like financial returns or economic data, they don't stick to this perfect script. They can get all lopsided or have these totally wild, unexpected swings. So, what do you do then? And that brings us to the first way data can get weird. Instead of being perfectly balanced, it can kind of lean over to one side. It gets a little awkward. The fancy statistical term for this is skewness, but really it's a super simple idea. It's just a number that tells you how lopsided your data is compared to that perfect bell curve we just saw. And this is a great way to see it in action. On the far left, you've got a right-skewed distribution. A perfect real-world example is income. Most people are clustered down at the lower to middle end, but you have this long tail stretching out to the right for a few super high earners. And then the chart on the far right is just the opposite, a left-skew distribution, where most of the data is piled up on the high end.
Now here's a really cool trick for spotting skewness. You look at three numbers, the mean, the median, and the mode. And that perfect bell curve, they're all the same, right in the center. But when the data is skewed, that long tail acts like a magnet, and it literally pulls the mean, the average, away from the center. It's a total giveaway that something's not symmetrical.
Okay, so data can be lopsided. Got it. But there's another, even more dramatic way it can be strange, and that's something called kurtosis. This isn't about the data leaning left or right. This is all about the extremes. It tells us how likely we are to get hit with a massive, out-of-the-blue surprise. You know, a black swan event.
This chart shows it perfectly. That red line is our old friend the normal curve. But check out the blue line. That's a heavy-tailed distribution. It's telling you two things at once. One, you're going to see a lot more results clustered right around the average. That's why the peak is higher. But, and this is the big one, you also have a much higher chance of seeing those crazy, extreme outcomes way out in what we call the fat tails. It's a world of mostly normal days, but they're punctuated by huge shocks. So if your data has heavy tails, you're living in the world on the left, prone to those sudden lightning strikes. The technical term is leptokurtic. On the other hand, if your data has thin tails, it's more like the world on the right. Everything's calmer, more predictable, with way fewer surprises. That's platykurtic. It all comes down to how likely you are to see those extreme events. Okay, so we've got a problem. Our data is skewed. How in the world do we model that accurately? We clearly need a better tool. So let's meet our first hero, the skew normal distribution. What's so great about this distribution is its simplicity. It's basically a normal distribution, but with an extra knob you can turn. That knob is a parameter called alpha, and it lets us dial in the exact amount of lopsidedness we need to match our data. And the logic here is super straightforward. You set that alpha knob to 0, boom, you get a perfect bell curve. You start cranking it into positive numbers, the curve gets skewed to the right. You take it negative, it skews to the left. And the further you get from 0, the more extreme that skew becomes. It's just a really elegant way to handle lopsided data. But hang on. What if your data isn't just lopsided, but it also has those wild, heavy tails we were just talking about? Well, the skew normal can't handle both at once. For that, we need to bring in an even more powerful tool, the skew t-distribution. The skew distribution is the next level up. It keeps that alpha knob for skew, but it adds a second control called degrees of freedom. And you can think of this as the tail fatness dial. The lower you set this number, the fatter the tails get, which means the model gets way better at predicting those rare, extreme events. And this is really why it's the ultimate tool. It's like the Swiss Army knife of distributions. It can be normal, it can be skewed, it can have heavy tails, or it can be all of those things at the same time. It's incredibly flexible, which is exactly what you need when you're dealing with messy, real-world data. All right, that's enough theory. Let's put these tools to the test. We're going to look at the daily returns of U.S. 10-year Treasury bonds over a 5-year period. So the big question is, does this data look like a nice, clean bell curve? Let's find out. Well, the numbers here pretty much speak for themselves. The skewness is over 2, so that's a really strong lean to the right. But then, look at the kurtosis. It's not just a little high, it's over 42. This data has incredibly fat tails. A normal distribution model doesn't even stand a chance here.
Let's just pause and stare at that number for a second. 42. Remember, a normal curve has a kurtosis of 3. This value is screaming at us that extreme outlier events happen way more often in this data than a simple bell curve would ever predict.
Okay, this is a special kind of chart called a QQ plot. It's basically a visual test to see how well our data fits the model. Think of it like this. That straight line is what should be happening if the data was perfectly normal. The little circles are what actually happened. And look, they peel away from the line like crazy, especially at the ends. That's a huge visual red flag that the normal model is a terrible fit.
So let's bring in our first fix. On the left is that bad fit we just saw. On the right, we've used the skew normal model. And hey, it's an improvement. See how it fixes that problem on the left tail? It's accounting for the lopsidedness. But, and this is a big but, it still completely misses those extreme positive returns on the right. It's only half a solution.
And now, the grand finale. This is the QQ plot using the skew2 distribution. And wow, look at that. It is a dramatically better fit. The points are hugging that line so much more closely all the way out into the extreme tails. And why? Because the skew-T can handle both the skew and the crazy kurtosis. It actually understands the real shape of this data.
You know, the researchers who did this analysis really said it best. The key takeaway is that you have to use the right tool for the job. If your data has thick tails, you absolutely have to use a model that sees them. If you don't, you're basically blind to the biggest risks.
So let's just quickly retrace our steps here. We started with a big problem. Real-world data doesn't fit the simple bell curve. We found a partial fix with the skew normal model, which took care of the lopsidedness. But the real winner, the best fit, came from the skew-T distribution because it could tame both the skew and those wild, unpredictable tails.
And all of this leaves us with a pretty heavy question, right? We just saw with our own eyes how badly the simple bell curve failed to describe real financial data. It really makes you wonder how many of the models that are used to predict our finances, our economy, how many of them are still using that simple, outdated tool? And if they are, what massive, crucial risks are they completely failing to see?